Good morning. Today the topic of our discussion is multi-component polymeric materials. When we talk about polymer technology, that is polymer product technology, we think of some products made of virgin polymer materials along with some functional additives. Now, there are certain limitations of that product technology made from individual homopolymers. So, there were enough reasons to find out improvement in the properties of the product. For that reason, people have developed some polymer products which are better than the products made from single polymer materials to develop a broad spectrum properties in the product. So, basically a need is felt for such type of products which are supposed to provide broad spectrum properties as well as better properties or improved properties over the properties contributed by a single polymer in the product. To explicitly explain, we know about the homopolymers, we know about the copolymers. The difference between homopolymers and copolymers lies in the fact that homopolymers are made from a single monomer. That means, the monomeric unit repeats along the entire backbone of the polymer chain and we get a polymer. Now, when the properties of that homopolymer is not sufficient enough to obtain the desirable performance of the product, then people thought about mixing a second monomer or a third monomer with the first monomer to form a new product which is known as copolymer. That means, polymers made or synthesized between more than one monomer, so that the monomer units of the different monomer units appear along the backbone chain in a different sequence. I discussed in other lectures, that is, the monomers when they are arranged in a alternating sequence or alternation sequence, that is called alternating copolymer, when the monomer units of two different monomer units are arranged in a block sequence, block of one monomer followed by the block of the second monomer, then we get block copolymer. Or the monomers, two monomers can be arranged in a random fashion along the backbone chain, that is called random copolymer. Not only that, there can be a graft copolymer, that means onto the backbone of one of the polymer of the monomer, a second monomer is polymerized, so that it is grown or starts from the backbone of the first polymer, so that the second polymer becomes grafted or becomes attached to the first polymer chain. So, that is graft copolymer. So, this way these copolymers were developed, and as it was expected that such copolymers are supposed to provide better products, properties or improved properties or broad spectrum properties, which is not present in one homopolymer. That was successful. That means the properties of the two monomers can be developed in a copolymer. Similarly, when people could not be further satisfied with this either homopolymer or copolymer, then people thought about multi-component blends of polymers. That means more than one polymers are mixed together. So, there are lot of science behind this copolymer synthesis, copolymer properties, and the science behind the multi-component blends or the blends of more than one polymer to form a new product. I have discussed to some extent in other lectures. Now, here when homopolymers from individual monomers should not or cannot provide the desirable properties or cannot provide broad spectrum properties, the need of tailoring the existing polymers to newer products was failed. So, people ventured to mix two more different polymers or to get two more different polymers or to get a polymer composition with a newer set of properties, or people tried to polymerize two or more monomers together with the other monomers to get a new polymer known as copolymer. So, this way the existence of or the development of copolymers and polymer blends were found. Now, what are the problems, or if there is any problems if we go through or if we go for synthesis of copolymers or the polymer blends. In case of copolymers, you know that the monomers, different monomers are attached to one another through covalent primary bonds or primary covalent bonds. So, basically that polymer made from two monomers are not a mixture of two polymers, rather different properties of different monomers are introduced in one polymer having the presence of two different monomers in a different sequence. In case of polymer blends, that is okay, that is good. In case of your copolymer, there is a success in developing newer properties, there is a success in developing broad spectrum properties. But when people went for mixing more than one polymer or two polymers or three polymers like this, then a problem was faced. So, when polymer 1 is mixed with polymer 2, P1 is mixed with P2, a product known as polymer blend is produced. Now, there are many considerations to be thought of in this particular issue. Now, what is the nature of polymer 1, what is the nature of polymer 2, how they are mixed, after mixing how they show the properties, or what about their phase, two different phases of polymer 1 and polymer 2, all these things are to be considered. In that angle, we have to discuss about the miscibility, immiscibility of the component polymers, miscibility, immiscibility of the component polymers. If the component polymers are not miscible, then what will happen? The phase 1 will separate from phase 2. That means there will be separation of different phases, presence of different phases. When it is produced by some process, initially we can have improved properties or the combination of properties or the addition of properties of polymer 1 with the polymer 2, but in the long run during service during the service of the product, during the use of the product, with time there will be separation into separation of polymer 2 phase from the polymer 1 phase. So, that leads to unstable or instability in properties. So, that is not a desirable phenomena. The product should maintain its properties for a longer period or even up to its end of life. So, miscibility, immiscibility, phase separation, these aspects are to be considered. If we discuss with examples, let us take the examples of homopolymers of ethylene, which is polyethylene PE. There are different grades, LDPE, HDPE, LLDPE, VLDPE, ultra high molecular weight polyethylene. So, those are all homopolymers, but the different grades differ from each other, differ from one from the other in terms of their microstructure, in their molecular weight, their branching, non-branching, density, so and so. Similarly, propylene also gives a homopolymer polypropylene. Same is the situation with polypropylene. So, these are known as very good plastics. As I mentioned, if we want to have a multi-component polymers, that means in one polymer there can be more than one component. Say we want to have ethylene component in the polymer along with the propylene component in the polymer. So, we can synthesize a copolymer of ethylene and propylene. So, it will form a copolymer of EP, EP, EP like this. So, if we place this ethylene and propylene units in alternation, we call it ethylene propylene copolymer. If we place these ethylene propylene units in the form of blocks, say ethylene block followed by propylene blocks like this, we call it block copolymer. This way it continues. If we want to graft ethylene propylene onto the main backbone chain of ethylene, it looks like this, from where this propylene segment can grow. This is graft copolymer. Similarly, we can have random copolymer, ethylene, propylene, propylene, ethylene. It is random. These ethylene units or propylene units are randomly placed in along the backbone chain of the polymer, random placement. So, random copolymer. Here in doing so, the properties of homopolymers are drastically changed in the copolymer because of the presence of the two monomer units in the backbone chain, and this copolymer of ethylene propylene becomes elastomeric in nature, whereas their homopolymers are plastic. Before going to discuss about this little details of this multi-component polymeric systems, we must look at the definitions of some terminologies. Sometimes we hear as polymer alloy. Now, this terminology alloy is used in case of metal alloys. Metals and alloys means that is a solid solution of one metal in another metal, that is a solid solution. Similar is the case for polymer alloy. So, we can consider that if one polymer becomes soluble in another polymer, that means one of the polymers can act as solute and the other polymer can act as solvent. In that case, we can get a polymer alloy. Again, if we take this example of polymer P1 and polymer P2, so this product will be a polymer alloy, provided they form a solid solution and there is a molecular mixing and the chance of separation into phases, all these things does not occur at all. So, that is called polymer alloy. Then what is polymer blend? Polymer alloy can also be called as polymer blend. Now, this polymer blend is a mixture of polymers, mixture of more than one polymer with other polymer, or mixture of a polymer or a copolymer and or mixture of two copolymers. So, polymer mixture, polymer mixture, copolymer mixture or polymer copolymer mixture. So, these different cases, different blends of polymer, copolymer forms constitute this polymer blends. Then what is miscible PB, miscible polyblend? It is a single phase polyblend system. It is supposed to be a single phase polyblend system at molecular level of dispersion of one polymer in other, and it must fulfill the thermodynamic criteria, that is heat of mixing of the two polymers should be negative. When delta H or M, that means heat of mixing of the two polymer is negative. Then other terminology also we come across, that is compatible polyblend. When the two polymer components mix, we get a polymer blend. There the question of these two components miscibility or the compatibility, phase mixing of the two component polymers or interfacial addition of one polymer molecule with other polymer molecule, that is known as compatibility. So, that and that leads to compatible polyblend, and it can be considered as a homogeneous system with enhanced physical properties, that is intimately mixed, molecularly mixed to form a homogeneous solution, homogeneous mixture. We can consider that as also polymer alloys, there is nothing wrong in it, and by doing so we can have improved or enhanced physical properties of the as well as the chemical properties of the polymer blend. Then comes, we want to make this compatible polyblend, then what are the means of compatibilization? What is the meaning of this term compatibilization? Now, any physical or chemical action which stabilizes a polyblend without phase separation is known as compatibilization. That means, a polymer B to be blended with polymer A to make it compatible, for that action there must be some chemical or physical interaction between the two component polymers, and that physical or chemical action must stabilize the system of the polyblend without any chance of phase separation. Now, there is another terminology is engineering polymer, EP, engineering polymer. Now, engineering polymer is also considered as a processable polymer, which is supposed to exhibit high performance properties, say high mechanical properties at certain temperature, where the product is to be continuously used or the product is to perform continuously, preferably at a temperature of higher than 100 degree Celsius with a tensile strength of greater than say 40 megapascal. So, a polymer which can stand higher than 100 degree Celsius for a prolonged service period, for a prolonged service, maintaining a tensile strength, tensile properties of the polymer beyond 40 megapascal. Then the terminology engineering polyblend EPB. So, to make engineering polyblend, we can take a polymer alloy or a polymer blend in which one of the components should be an engineering polymer, that is known as engineering polymer blend. So, a polymer blend, once again I repeat, a polymer blend having components PA, polymer alloy or polymer blend, either of these two, any of these two should be an engineering polymer, that is known as engineering polymer blend. If we look into the classification of this polymer alloys and blends based on their miscibility or their degree of miscibility, degree of mixing, degree of compatibility, etc., the miscible blends should behave as homopolymer. This one of the classes of this polymer blends and alloys. This miscible blend should behave like a homopolymer. That means, it can be considered as a substitute of homopolymer. At the same time, having higher level of properties over those of homopolymers, as well as development of newer properties which is not available in the homopolymer, and their properties are composition dependent. That means, the properties of the blend is dependent on the composition of the component polymers. That means, whether the property available is dependent on 70-30 basis, that means, one component is 70 parts by weight or parts by volume, and the other component might be 30 parts by volume or parts by weight. Now, if we move from the 70-30 to 80-20 or 90-10 or 60-40, the properties of the blend, may vary. In fact, it happens. So, in order to optimize that, one should make blends in wide range of compositions to arrive at the maximum property available from a suitable composition. It might be 60-40 or 70-30 or 50-50, that is to be explored. Next class is immiscible blend. Now, this immiscible blend is a mechanical mixture of two immiscible polymers. Here we must understand that the two component polymers are not miscible, and we are blending it, mixing it, and the product formed is known as immiscible blend. So, mechanical mixture of two immiscible polymers and commercial products are made via careful control of morphology. For example, polyethylene terephthalate. Polyethylene terephthalate nylon 66 blend for that is used for monofilament application. Now, this polyethylene terephthalate and nylon 66 are not completely miscible. There are certain immiscibility effect of these two polymers, because the two polymers are chemically different. Still then, since these two polymers are little polar in nature, through polar interaction they can be used for making a blend, but their properties can also be modified or toughened with engineering reagents containing 2 to 4% of the polyolefin or rubber. So, these polymers can be blended, compatibilized with a mixture of small percentage of some other polymer, that can be polyolefin, say polyethylene or polypropylene, or a rubber. Next class is compatibilized polymer blend. When two component polymers are not compatible in a mixture, in a blend, well, we can also use those component polymers P1 and P2 to form a blend with the help of a third material ingredient, we should say, that is known as a compatibilizer. We can consider, or we can designate this compatibilizer as a marriage maker. That means P1 and P2 does not like to mix with each other, but since because of the difference in their solubility parameter, their polarities and their other aspects, molecular weights, densities, so and so, these two basically immiscible components can be made miscible if a third component, third person is brought in between them, which is known as a marriage maker. That marriage maker is known as compatibilizer. So, with the help of a compatibilizer, two immiscible polymer can be converted to a polymer blend. Now, this modification is done, such modification with the help of compatibilizer is done by addition of an agent which is known as compatibilizer, this compatibilizer interact with both the phases. So, this can be a block or graft copolymer, this can be a ionomer, this can be a co-solubilizer, means a co-solvent type of thing. That means, the third component which is used as compatibilizer can interact with the both, so that they can keep both the polymer components P1 and P2 miscible by the presence of this third component. Examples are polyphenylene oxide PPO and polyethylene, these two, and these two are compatibilized. Polyethylene is purely hydrocarbon, polyphenylene oxide has got some polar nature. Now, that is compatibilized with the help of styrene, ethylene, styrene, co-ethylene, co-butylene copolymer. So, because of the presence of this phenyl ring of styrene, presence of ethylene unit, presence of butadiene unit, so these help to make these two component polymers miscible. So, this is known as SEBS. So, SEBS can be used as a compatibilizer, can act as a compatibilizer. Then comes this block copolymers, block polymers and their blends. These block polymers and their blends, these are basically made up of macro segments of different nature, say polyurethane, polyether imide, polyether block amide, polyether block amide, etc. So, these polymers have macro segments, means segments are the molecular weight of that segment is higher than that of a monomer unit. So, that is why they are known as macro segments. So, that is known as block polymers and their blends. Say styrene block styrene butadiene block copolymer SBS, also SBS. Similarly, polyether polyurethane, polyester polyurethane. Similarly, carboxyl terminated polyurethane, carboxyl terminated polybutadiene. There can be many examples to be cited in favor of that block polymers and their blends. So, there are so many block polymers, they can be also blended to form a new product having newer set of properties. Let us look into some commercially available polymer blends or commercial blends. There are plenty of examples. You can get details of those examples in other literature. Just to mention examples of few, say Lexan is the trade name, producer is manufacturer is General Electric Company, and the component polymers in that blend is polycarbonate and polyethylene. You see, it is fantastic. Polycarbonate is a polar polymer, it is an engineering polymer. Polyethylene is a non-polar polymer paired with hydrocarbon polymer. Now, the purpose behind the blending of these two polymers is that this polarity of this polycarbonate is altered by the presence of polyethylene, or the hydrocarbon nature, non-polarity nature is altered by the presence of polycarbonate. So, by varying the composition of polycarbonate and polyethylene, we can have some new properties in some particular composition. So, this blend is available in the market. Similarly, Noryl, it is a polyphenylene oxide and high impact polystyrene blend, mixture of high impact polystyrene with polyphenylene oxide. Vectra, produced by Celanese Corporation, it is basically a liquid crystalline polymer blend. More than one liquid crystalline polymers are mixed to develop a composition which is better than which have better properties than individual liquid crystalline polymers. Ultem, again manufactured by General Electric, it is a polyether imide blend with thermoplastic polymer. Polyether imide is a blend with TP, thermoplastic polymer. Loranil, made by BASF Germany, polyphenylene oxide, polyphenylene ether with thermoplastic polymer. Nidur is polyamide with an elastomer. Texin, Mobe is the manufacturer, polyurethane polycarbonate blend. Then Celanex, made by Celanese Corporation, it is a blend of polybutylene terephthalate with polyethylene terephthalate. Crelastic, made by Uniroyal Company, it is a blend of acrylonitrile, butadiene, styrene tar polymer and PVC, polyvinyl chloride. So, there are plenty of examples where the commercial products are available from the blends of different polymers, say with polyolefin and with some other condensation polymers. So, these are the few examples only shown over here. Now, to talk about the compatibilization techniques or the principles of compatibilization of the polymer blends, that is done to prevent segregation of the component polymers in the blend by promoting co-crystallization between the component polymers. That means, these polymers, when they are processed by melt processing technique, means they are mixed, then they are fabricated either by injection molding or by compression molding or by transfer molding. Then after filling the mold, the polymer filled mold is cooled, the rate of at a specified rate of cooling. Now, that specified rate of cooling affects this molecular alignment or organizes these molecules to have this long range order in the product. So, either to develop crystallinity or either to crystallize or non-crystallize or to remain or to keep it in amorphous condition, that depends on the requirement. If it is required that the products are to be or the polymer molecules are to be crystallized in the product, that means molecularly aligned to develop long range order, molecular order, then the cooling rate is properly adjusted so that polymer molecules crystallizes. So, that is a phenomena of crystallization during cooling of the product within the mold. Now, that principle has been used as a method of preventing segregation of the component polymers in the blend by promoting co-crystallization. Now, the crystallization phenomena is a kind of purification, we know, kind of purification technique, means that one material can be purified by crystallizing in presence of other impurities. So, after crystallizations these impurities are removed. Now, here in this case one polymer is supposed to be crystallized in presence of the other. That means, the nature of the two polymers are chemical nature, structure, etc., are almost comparable or identical. Then two segments of the two different polymer molecules can crystallize together. That means, form a crystallite in which one can find the presence of the two different component polymers, that is known as co-crystallization. So, such co-crystallization can help to prevent segregation of the component polymers in the blend. This is a kind of, this is one of the principles of compatibilization. Second is the cross-linking of the dispersed phase. Say we want to make a blend of polymer 1 with polymer 2. So, if we consider that polymer 1 is the major phase, suppose it is 70 parts by weight, 70 parts by weight polymer component 1 polymer, with which we want to mix component polymer 2 having 30 parts by weight. So, this P2 will, since it is used at with lower concentration, this P2 will remain dispersed in the phase of P1. In this case, P1 will behave as a matrix, the continuous phase, and P1 P2 as dispersed phase. Now, this dispersed phase can be cross linked, means this is the phase of P1 molecules in which these P2 molecules are dispersed lower concentration than the P1. So, these are P1 molecules, so these are P2 molecules, P2 molecules, P2 molecules. Now, if these are intimately mixed, P2 molecules are intimately mixed in P1 phase, that means P2 is dispersed in P1 phase. Now, if these P2 molecules are interlinked, only P2 molecules are interlinked. So, what will happen? These P1 molecules will remain in the cross-linked phase of the P2 molecule. So, that is a kind of compatibilization. That means, if P1 wants to go out of this P2, P1 molecules likes to go beyond this P2, go from the P2 site, then that will be prevented, since there is a network formed by P2 and this P1 is entangled with this P2 network. So, P1 cannot move from P2 to separate into a different phase. So, that can prevent phase separation or segregation. So, this is a kind of compatibilization technique by cross linking. Then forming interpenetrating network. So, this formation of interpenetrating network is again a extension or modification of this cross linking of the dispersed phase in the phase of P1 continuous phase. Okay. So, this interpenetrating network means we can have a polymer, I will discuss later, IPN. We can have a network of one polymer system in which we can grow another network by polymerizing a second monomer in this. So, it will form an interpenetrating network like this. So, that is also another way of compatibilizing the two components. Then ionic interactions, say polar interactions. Say one polymer can have some ionic group, say P1 can have some ionic group. Now, the ionic groups of P1 can be interacted with some other ionic group, of P2. That means, the ionic groups of this P1 and P2 are not identical, they are different, but they are ion, since they are ionic, say positive or negative ions. So, say positive ions of P1 can interact with the positive negative ions of P2. So, that is called ion-ion or ion dipole interactions that can also stabilize the two different phases in a blend of two component polymers. Next is hydrogen bonding. It is a secondary interaction. Hydrogen bonding is again secondary interaction. Through secondary interaction, hydrogen bonding, one can stabilize the segregation or prevent the segregation of the component polymers. That means, hydrogen present in one polymer linked to some more electronegative atom, and hydrogen present in another polymer linked to some electronegative atom. So, there will be competition of hydrogen bonds between the electronegative atom present in one polymer with the other present in the different other polymer. Okay. Then the second principle is use of compatibilizer. As I mentioned earlier, that compatibilizers can be of different nature. This compatibilizer can be block copolymer, or graft copolymer, or co-solvents. I shall discuss little elaborately later. Then compatibilization through reactive polymer processing. Reactive polymer processing means one polymer can be one of the component polymer, suppose it is P1, can contain some functional groups, functional sites. Again, component polymer P2 also contains some other kind of functional groups. So, these two different functional groups can in different functional groups present in P1 and P2, they can react with each other to form a new product, and through such reaction this separation of phase P1 from the phase 2 or separation of phase P2 from the P1 can be prevented, or even monomer of P2 can be polymerized in the matrix of P1. Okay. That is a technique known as polymerization. Through polymerization, we can also go for compatibilization, which is known as one of the techniques of reactive polymer processing. Functionalization. One can functionalize, say, component polymer P1 and P2. These two polymers are available in the market. I want to develop a new product P having different properties from that of either P1 or P2. So, I can chemically modify this P to P prime, I can chemically modify this P1 to P1 prime. Similarly, I can also chemically modify this P2 to P2 prime. That is done through functionalization of P1 and P2. That means chemical modification of P1 and P2. For example, we can say halogenate polymer P1. That means halogen atoms can be added to polymer P1, so that it becomes P1 prime halogenated polymer, and we can also we may or may not modify the speed. Suppose if it is a halogenated polymer, then we can mix this P1 prime with P2. P2 is a halogenated polymer, we can mix this P1 prime with P2 through halogenation of this polymer P1. So, P2 contains halogen atom, P1 does not contain halogen atom. So, we can add or attach some halogen atom so that we can blend this P1 and P2. Not only that, we can attach some other functional group, say we can carboxylate, or we can develop hydroxyl groups, or even we can develop some free radicals in either of these two polymers. We can blend, then we can make a blend of these two polymers P1 and P2, and which will be stable in properties. Then polymer reactions. Now, polymer 1, as I mentioned earlier, this polymer 1 can have some functional group, and polymer 2 P2 can have another functional groups of opposite nature. So, if they are opposite nature, then these two functional groups functional group of P2 can react with P1, and these two polymers can interact with each other, and the new product the product will be a new material having different properties. Then semi interpenetrating network, this is also another technique by which we can develop new properties in this, or we can compatibilize these two polymers. Again, we can view this polymer blend in different way. We can have polymer blend, that means homopolymer blend. We can have a blend of polymer and copolymer. We can have a blend of copolymer and with a copolymer. Now, these polymer blends, different types of polymer blends, in which the component polymers can be either miscible, or the component polymers can be immiscible. Now, if these component polymers are miscible, then that can again be homogeneous or can also be heterogeneous. So, depending on our requirement, we can make homogeneous miscible blend as well as heterogeneous miscible blends. Then, if the component polymers are immiscible, then we have to take certain measure, adopt certain measures, or do something on the component polymers, so that the two component polymers can be miscible. That is done through compatibilization, and ultimately we get a polymer alloy or solid solution of two different component polymers. This way we can get multi-component polymer systems from two different component polymers, polar, non-polar. They can lead to miscible polymer blends. Now, a blend of a polar polymer with a non-polar polymer can be miscible. We can make it miscible through compatibilization. Similarly, we can mix a non-polar polymer in a polar matrix through compatibilization. This way we get polymer alloys or polymer blends or polymer mixtures. So, in next lecture we shall discuss the other aspects of these multi-component polymer systems. Thank you.